Welcome back to the Explainer. So in our last one, we saw how limits are kind of the secret engine helping us find instantaneous speed. But why did we need a brand new tool just to find speed at a single instant? Well, traditional algebra, it needs two distinct points to calculate speed or slope. If you try using just one point, you end up dividing by zero and, well, algebra just grinds to a total halt. Today, we're shifting gears from instantaneous speed to decoding the ultimate superhero tool of calculus, the limit itself. Think of it like a mathematical magnifying glass. If algebra is a static snapshot, giving you moments frozen in time, calculus is the whole motion picture. And the limit? It's the specialized lens that actually lets us see that continuous motion clearly.
Here's our roadmap for today's investigation. We'll start with what is a limit, move to the numerical table method, then the strict rule of limits, two sides of the story, when calculators lie to you, and wrap it all up with the final jump challenge. Let's get right into it.
Part 1. What is a limit? Investigating the neighborhood. Let's kick things off with the foundational question of our whole investigation. What exactly is a limit? We really need to reframe this. It's not some boring, static formula you just memorize for a test. It is an active pursuit of a destination. In regular algebra, everything is static, right? You plug a number in, you get one defined number back. It's black and white. But calculus? Calculus is the math of motion and change. We want to know what a function is trying to do. What destination is it heading toward, even if it never actually arrives?
Formally, the definition looks like this. You read the notation as the limit of f of x as x approaches a equals L. What this means in plain English is that as our input, x gets closer and closer to a specific number a from either side. The values of our output, f of x, get closer and closer to the number L. The absolute key takeaway here is that we are talking about the neighborhood of a, not a itself. This formally sets up our investigation. As our input shrinks the distance to a certain point, what destination is the output zooming in on?
Which brings us to Part 2, the numerical table method, gathering the clues. Now, let's investigate our first major suspect, a function with a hidden hole that totally breaks traditional algebra. Let's look at this specific function, x squared minus 1 all divided by x minus 1. Notice exactly what happens if we try to plug in the number 1 for x. The denominator becomes 1 minus 1, which is 0. Yep, we're dividing by 0. As anyone who's taken algebra knows, this is where math traditionally throws its hands up in the air. That means algebra fails us entirely right here. The function is completely undefined at that exact coordinate. Hitting a dead end like this is incredibly frustrating in standard math. But remember, calculus does not care about the point itself. Calculus has a brilliant workaround for this exact scenario.
And this brilliantly illustrates James Stewart's numerical table method. Imagine actually punching these numbers into your calculator. By calculating values closer and closer to 1 from the left side, plugging in 0.5, then moving closer to 0.9, and then getting super close with 0.999, and then coming in from the right side, starting at 1.5, moving to 1.1, and edging right up to 1.001, we see a highly predictable pattern emerge. Look at how tightly these numbers squeeze the output towards 0.5. An input of 0.999 gives you an output of 0.999. An input of 1.001 gives you an output of 1.001. The values of f of x are clearly approaching 0.5 from both directions. This numerical pattern tells us that the limit absolutely exists, even if the function has a literal hole right at that exact coordinate. We don't need to step into the hole to know exactly where the road was leading. The table reveals the destination without ever touching the undefined point.
Moving to Part 3, the strict rule of limits, the golden rule of evidence.
We've successfully sneaked up on our point, which brings us to the absolute golden rule of this investigation, straight from Stewart's text. Quote, notice the phrase, but x does not equal a in the definition of limit. We never consider x equals a. The only thing that matters is how f is defined near a. Finding the limit of a function as x approaches a never ever depends on what happens exactly at a. Think of it like a broken bridge spanning a river. You know exactly where the bridge should be connecting based on the road leading up to it from both sides, even if a massive chunk of the actual bridge is just gone right in the middle. Whether the actual point is there, missing, or magically teleported somewhere else, the limit only cares about the intended destination. This rule is exactly why calculus can step in and solve problems that algebra simply cannot touch.
Part 4. Two sides of the story. Conflicting testimonies.
But what happens when the left side and the right side point to completely different destinations? Sometimes the direction you're traveling completely changes the answer. If we approach our target from the left, we call it a left-hand limit. From the right, it's a right-hand limit. Notice the specific notation here, which definitely trips students up at first. That tiny minus or plus sign acting like a superscript next to the A tells us our direction. A minus sign means we're approaching from values less than A on the left, and a plus sign means we're approaching from values greater than A on the right. Here's the catch. For a general, two-sided limit to exist, both sides absolutely must agree on the exact same value. Imagine a classic step function, sometimes called a heaviside function, or just picture a staircase. Think of a sudden step on that staircase, or flipping a light switch from 0, which is off, instantly to 1, which is on. If you approach from the left side, you're at 0. Approach from the right side, you're at 1. The left hand touches 0, the right hand touches 1. Because they point to completely different numbers, they refuse to shake hands. They don't meet in the middle to form a valid limit. When this happens, we declare that the general limit does not exist.
Part 5. When calculators lie to you. The deceptive witness.
This brings us to a really fascinating part of our case, and a major warning for all calculus students from James Stewart. Do not always trust the calculator in your pocket. Let's investigate this wildly oscillating function, sine of pi over x, as x approaches 0. Human nature makes us want to just trust the machine's convenient decimals, right? If you just punch a few random easy numbers into this, like 0.1 or 0.01, you might wrongly guess that the limit is simply 0. The calculator repeatedly spits out 0 for those specific inputs, so case closed, right? Wrong. As you zoom in toward the origin, the function actually goes entirely crazy. Because x is in the denominator, as x gets infinitely small, the fraction gets infinitely large. This forces the sine wave to compress and just start jumping infinitely often between 1 and -1. Calculators fail us completely here because finite sampling tricks the eye. They only plot points every so often, completely missing these rapid, infinite oscillations. Plus, zooming in too much on digital tools causes false convergence and inaccurate graphs because of internal subtraction errors. Because it's jumping infinitely often, there is no single destination, and therefore the limit does not exist. You always have to use your brain and your graphs together.
What's truly fascinating here is a real lab project from Stewart's text. Complex trigonometry can completely trick even advanced computer algebra systems. It's proof that you absolutely must use your analytical graphing skills and your calculus foundation. You literally cannot just rely on a machine's raw computation when the concept of infinity is involved, simply because machines are finite by nature.
And finally, Part 6, the final jump challenge. The case is yours. You are now fully equipped with the analytical tools of a calculus detective, so I'm turning the case over to you. Challenge time. I want you to picture a scenario. Really visualize it. Imagine the left side smoothly approaches a height of 5. The right side also smoothly approaches a height of 5, but there is a solid dot dropped completely out of place on the graph, sitting way down at the coordinates 3, 1.
Based on everything we investigated today, what is the limit of f of x as x approaches 3? And conversely, what is the actual defined value of f of 3? Hint, remember our strict rule about whether the limit cares at all about the actual point itself. Post your answers in the comments below. And join us in the next explainer where we'll uncover the analytical limit laws so we can solve these mysteries without ever needing to build a numerical table again. Keep questioning, keep learning, and I'll catch you next time.